Why do we need to integrate different data sets? To address this question, let's take a look at the following two examples. In our first example, let's process an electrical resistivity data using different inversion algorithms and different inversion settings. Here we have 6 models. Models 1 to 4 were generated using our resistivity inversion code, whereas models 5 and 6 were generated using 2 other commercial codes. The models have different resistivity range or different resistivity structure. Furthermore, all the models show small data misfit errors. That means the theoretical resistivity data obtained from each model is highly consistent with the measured resistivity data. So which model is the closest to the real model? We will address this question using the first 4 models belonging to our resistivity code. To assess the quality of the models, first we need to calculate the model resolution. Model resolution indicates to what degree the recovered model parameters are determined by the initial resistivity model. The model resolution plots for the resistivity models 1 and 2 show good resolution up to about 5 meters deep, while models 3 and 4 have bad resolution throughout the model's domains. Therefore, models 3 and 4 are no longer considered valid models. Models 1 and 2 show similar resistivity structure, but completely different resistivity range. To address which one is better, we need to calculate the model information content. Model information content indicates to what degree the model parameters are influenced by the measured resistivity data set. The information content of Model 2 is higher than Model 1, therefore Model 2 is better. As a final processing step, we re-inverted the data set, assuming Model 2 settings, and using a grid that is 5 meters deep. The obtained optimum model has much higher information content value than Model 2. Will data integration improve the model information content? We will address this question in the following example. Our second example is the geophysical data integration using the disconnect inversion approach. The disconnect inversion is a modification of the classical smoothness constraint inversion to accommodate sharp boundaries. This method requires that the boundary of the target be known a priori, for example, from borehole logs, geological or other geophysical sections. In this example, we will use a seismic model to define the location of the disconnected boundary in the resistivity inversion. We will choose the 800 meter per second seismic velocity contour to define that disconnected boundary. The obtained model from the disconnect inversion has higher information content than the optimum model obtained from our previous example. Furthermore, it has a better resistivity structure and is more consistent with the actual resistivity model. An alternative geophysical data integration approach is the joint inversion technique with the cross-gradient constraint. This approach is centered around the general idea that different geophysical methods collected at the same locations will show structural changes at the same subsurface positions. Joint inversion searches for subsurface models by simultaneously fitting data sets from different geophysical methods, while the cross-gradient constraint maximizes the structural similarities between different models regardless of the physical parameter values of each model. The image shows the step-by-step derivation of the cross-gradient function and its derivatives using forward difference scheme. Here is a joint inversion example between frequency domain electromagnetic induction and seismic refraction data sets. The upper 2 images are the actual seismic and conductivity models, the middle images show the recovered separate inversion models, whereas the lower images show the recovered joint inversion models. The video shows plots of the recovered models following each inversion iteration. As expected, the joint inversion models are structurally similar, and are more consistent with the actual models than the separate inversion models. Check out our remote data processing services at our website, www.geobridging.us. If you have questions, please contact us via email at contact@geobridging.us.